Are you ready? Okay, so let's start. No, 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 no. Okay, yeah, okay, yeah. Mute.
Sorry. Okay, sorry. Okay, can you hear me now? Thank you for your coming, ladies and gentlemen, and thank you, Akaki Sensei. Today, I would like to present my thesis defense, PhD defense. The title is Dimensional Speech Emotion Recognition by Fusing Acoustic and Linguistic Information. So, this is my arrangements for my today's presentation. I divided my presentation into 6 parts from introduction to conclusions. So, let's start with introduction. For the background of my research, I will show you two figures. First is this human-machine communication. In this figure, the left part is speech chain from human listener, and the right part is robot or machine as listener. So in speech, actually, we want to convey a message from listener, from speaker to listener. The message includes the emotion, and the process starts from our brain. We think what we want to say and then put it into linguistic form, and then the brain will send this message into vocal muscle along with motor nerve in form of impulse signal, and then our vocal organ like tongue, lips, and also vocal muscle will make movement, and then sound are generated, and then the sound are received by machine or by computer. So in this speech chain, there are 3 levels of information changing from linguistic to acoustic via physiological level or physical function. So my idea is by fusing a linguistic and acoustic information, because both information are correlated, it will make robot or machine easier to understand human emotion. So that's the first background. And the second background is about multimodal affective computing. Affective computing, according to Picard in 1995, he coined this term, is computing that relates to arises from and influence emotion. And in this figure, we can obtain or gather some data, speech data and visual data. And for speech data, we can split into linguistic information in text transcription using automatic speech recognition or ASR, and also we can directly obtain the acoustic feature or acoustic information. And in visual data, we also can split into some kinds of data like body gesture, facial expression, head movement, and maybe also others like hand movement and other part of body movement. And instead of using single information or unimodal information, we can combine all of the information. This what's called by information fusion. So the fusion of information from different sources or different sensors. So in this case, the acoustic feature extractor or linguistic feature extractor acted as soft sensors. And by this two figure or two background, I defined my research goal as follows. The main goal is to investigate the necessity of fusing acoustic information with linguistic information for dimensional speech emotion recognition or SER. And to achieve this main goal, I addressed 3 sub-goals. The first is maximizing the quantity of acoustic-only speech emotion recognition. The second one is fusing acoustic and linguistic information at feature level, or FL, called also as early fusion. And the last one, the third goal, is fusing acoustic and linguistic information at decision level, or DL, also called known as late fusion. And for a summary of this presentation, first is I show the novelties of significance of this research. So I discriminate between novelty and significance. Novelty is the new method, proposed method, while significant is the discussion or the previous finding resulted in this research. So I also divided into 3 according to sub-goals. The first is speech emotion recognition from acoustic information only. In this first sub-goal, I proposed 2 methods. The first is silence feature calculation, and the second one is acoustic feature aggregation. I will explain it later. And in early fusion, I proposed multitask learning based on CCC loss, concordance correlation coefficient. with some different number of parameters. And for the last rate fusion approach, I propose two-state processing to predict dimensional emotion recognition by combining DNN, deep neural network, and SVM, support vector machine. And for future application, this research may contribute to the following areas. The first is the main target is call center application. In call center application, this research can be used to measure the emotion of caller. For example, if someone complaining or calling call center or service center, usually they are complaining about something. So the operator or the staff, by using this speech emotion recognition, can obtain the emotion of the caller of the or the customer. So they can take a further step to make the customer calm down. Also, this emotion recognition also can be used to measure the satisfaction of the caller or the customer. Usually, if someone angry, if at the end they are happy, so they are satisfied with the service provided by the company. And also, not only to measure the emotion of caller, it also be used to measure the performance of operator. So the company can measure the performance of operator by measuring their emotion during the dialogue between caller and customer. So not only for caller, it's also useful for company to measure the emotion to judge to measure the performance of their operator. I think some telecommunication company now trying to implement this one, like NTT, and not only for call center application, the other target is for voice assistant. Nowadays, we use Alexa, Siri, Google Now, and Cortana, and these devices can recognize our speech well, but maybe only some now trying to obtain the emotion from user. I think that the Amazon Alexa now trying to make their device be able to recognize the emotion. So this is also important because if the device can monitor our emotion, we can also measure our well-being, in this case our mental well-being, and we can make some improvement for future, for time to time. And not only those two technologies, but also other technologies that related to speech, like voice message and voicemail, can benefit from this research. And that's for introduction. I will move to the second part, research methodology. The first is motivation. So why I'm researching speech emotion recognition, why I didn't use other visual or other data. The first reason is, in some cases, only speech data could be obtained. Like in previous scenario, like in telephone application, the only data can be obtained only speech. So we only use speech to recognize the emotion. And then the second one is there is evidence, strong correlation between speech and emotion. For example, Mairano et al. In 2019 show that pitch are related to valence, highly correlated valence, while rhythmic and spectral information are related to arousal. So by using these two reasons, I conduct my research in area of speech emotion recognition. And then why researching speech emotion recognition is difficult? The reason is because the labels are not exact. It is given by annotators. So compared to the speech recognition or image recognition, the labels are exact. For example, in speech, in the word transcription is exact. In image also, the label is exact, like dog or cat or car or truck and others. For example, in this table, I show you one excerpt of IMOCAP data set. In this data, 3 annotators are requested to annotate the data. I mean the label of speech, which is categorical emotion and dimensional emotion. In this dimensional emotion, the first annotator rated the valence score as 3, and then the score of arousal 2, and the score of dominance 2, while the second and the third annotator give the different scores. So it is difficult to judge the true label here because we don't have any true label because there are more than one label. So usually we use the mean value of some annotators, for example, 3 or maybe 5. The more is better, and we measure the agreement between writers. If the agreement is high, we can use this one. Otherwise, we cannot use this one. So that's why the speech emotion recognition task is difficult compared to other tasks because we cannot achieve the perfect accuracy, while in others we can obtain as high as accuracy. The next is why I did my research in dimensional emotion rather than categorical emotion. So there are three reasons here. The first is due to the high variability between human and human. So between human and human, the variability is high, so it doesn't make sense, or it's not have an essence to use category between one human to human to make the commonalities. And the second one is categorical emotion is not enough to describe the affective state. For example, if we know the category of emotion like angry, we don't know the level of angry. It is lower angry or high angry, we don't know. But using this dimensional approach, we can obtain such value, the score like from 0 to 5 or 1 to 5. And the last reason is conducting this research in dimensional is because most previous research only focus on categorical emotion because it is more practical maybe for in implementation. So that's why I conduct my research in area of dimensional emotion rather than categorical emotion. And the next is why I conducted my research by fusing acoustic with linguistic information. The simplest answer is because we can also obtain linguistic information from speech. So using ASR, we can transcribe speech into text, and then we can obtain linguistic information from text transcription. And also from research in psychology, it is evidenced that human communicate emotion through speech and language. For example, if someone angry, they tend to use certain words rather than other words. So because there is correlation between speech, emotion, and language, so I propose to fuse acoustic with linguistic. And the last reason for this motivation of using acoustic in linguistic is that because if we use linguistic, we have the data is doubled. So based on the previous research, more data tends to be more effective. So that's the reason why I've used acoustic with linguistic. And next is what research issue to be solved in this research. So based on the literature study, I found several issues in speech emotion recognition. I highlight 5 important issues. The first is region of analysis to extract acoustic features. And then second issue is the effect of post-processing in emotion, and I choose silence in this case. The third one is low valence prediction in dimensional emotion recognition, only in dimensional in this case. And the fourth issue is necessity to fuse acoustic information with other modalities. And in this case, I choose to fuse acoustic with linguistic because previous reasons. And if we consider this fourth issue is important, so another issue rises. That is the fusion framework for fusing acoustic and linguistic information. So I choose these 5 issues as to be solved in this research. And this is correlation between main goal, sub-goals, and the previous issues. So the main goal is to fuse acoustic with linguistic, and then I divide it into 3 sub-goals. And this correlation between each sub-goals with issue. For example, the first sub-goals related to the first and second issue, while the second and the third sub-goals related to the third, fourth, and fifth issue. And move to the concept or philosophy I used to solve this research. So the belief in this research is different from the previous research in speech emotion recognition. In previous research, the belief is emotion is related to how we say it. But in this research, the belief is it is not only how we say it, but also what we said related to emotion. How related to acoustic, and what related to semantic or linguistic. So using approach from information science, the flow of information from data information knowledge, or known as DIK, I figure out my research concept as in this figure. So we extract information from data and we extract knowledge for information. So this is inside a computer, and I resemble this approach to my problem in speech emotion recognition. The data is speech, the information is acoustic and linguistic, and the knowledge is the degree of dimensional emotion. And to extract acoustic and linguistic information from speech, we use feature extraction here. And to extract a degree of dimensional emotion, we use regression process here from acoustic information. So let's dive into each of one concept here. The first is data. The data is speech. According to the Oxford Dictionary, speech is defined as the expression of or the ability to express thoughts and feelings by articulate sound. So from this definition, we also see the relation between linguistic express thought is represented in linguistic, and then the feelings related to emotion, and articulate sounds is related to acoustic. And from speech, we also can obtain several information or precisely knowledge here. For example, using ASR, we can obtain the text transcription. For example, this speech transcribed into that's out of control. And then we also obtain the language information. The language here is English. And then the dialect here, the dialect is US English. And then also the gender. We can recognize the gender of in speech. Gender is female here. And also we can find the speaker who speak this speech. The speaker is the second speaker from the data set. And also we can predict the age of the speaker here, the age between 25 until 54 years old. And also my main interest is to recognize the emotion within speech. For example, in this case, in this utterance, the emotion is angry with valence 1, arousal 4, and dominance 4. And move to the second level in the professor hierarchy is information. The information is acoustic and linguistic features. So in this research, I saw the main information is acoustic information, while the linguistic is the additional information, because we can directly obtain the acoustic feature, but for linguistic information, we need ASR, or speech to text transcription. And this conceptual information in practice is implemented as features. So we need acoustic feature and linguistic feature. And commonly, acoustic and linguistic feature divided into two groups. The first is handcrafted feature. So we calculate manually acoustic features from speech. And other are using deep learning model. We apply model to speech data set and then directly obtain the representation, in this case, the acoustic feature. And also we can divide it handcrafted feature into two. The first is LLD, low-level descriptor, like F0, energy, Foreman, spectral information, and others. And also, instead of obtaining LLD, we can calculate the statistical function. So it is called as high-level statistical feature. So in this case, we only calculate mean value, max value, standard deviation, variance, and other statistics function. So this also called as LLD is also called as low-level feature, because we extracted on low area, local region in frame-based processing, while HSF also known as global feature, because we compute in one utterance. And using deep learning, we can obtain such feature representation. Usually it is called with the name of deep learning model, like deep spectrum, ResNet, or SONNet, or others. And in linguistic feature, it is similar. We divide it into two groups. The first is handcrafted feature, including the number of words, exclamation, negation, word number, time frequency, and others. And also using deep learning model, we only apply model to data set, for example, to Wikipedia or web crawl. So for example, in this case, is word to vector, ilmu, glove, fast text, BRT, and others. And the next hierarchy level in the hierarchy is the knowledge. So the knowledge here is the degree of dimensional emotion. So in emotion recognition research, there are two approaches. The most common is two approaches. The first is categorical view, like angry, happy, and others. And the second approach is dimensional view. So dimensional emotion in this case is emotion as continuous degree in several attributes or dimensions. And the most common dimension are valence, degree of pleasantness from positive to negative, and then arousal, degree of activation from sleepy to awake, and then the last one is the dominance, the degree of power control. There's also another model, but the most common one is this model. And according to Russell, he argued that the categorical emotion can be derived from valence arousal space, like in this picture. So if we know the degree of arousal and valence, it is possible to obtain the categorical emotion. For example, if valence high, arousal high, so maybe he's happy here. But if we add one more information, in this case dominance, it will more informative than the previous one. So we also know the degree of how can the speaker control their emotion. And according to Professor research, the most important here is valence, and then arousal and dominance. And also there are the fourth dimensions, but it's not commonly used until now. And move to research strategy. So I transform my research goal, which is 3 sub-goals, into 3 strategy. The first is dimensional speech emotion recognition using acoustic features. I divided this strategy into 3 to evaluate the 3 issues. The first is region analysis. The first issue, which is it is frame-based processing, a local feature, or statistical function using a global feature. And the second is effect of silent pause regions to represent the effect of post-processing. For example, if we remove silence or we use silence as additional feature, what is different? And the last one is the aggregation methods from chunks to utterance. For example, in speech, usually speech is long, for example, 5 minutes, but when processing speech, we split it into chunks, meaning that some smaller time than utterance. For example, 10 seconds, 5 seconds, or 20 seconds. So it is necessary to aggregate from chunks to utterance, and two methods are commonly used. The most commonly used is the majority voting or by output aggregation. And in this case, I also propose to evaluate the feature aggregation or input aggregation. And the second sub-goals I transformed into the second strategy is early acoustic linguistic fusion, or called as also as a feature level fusion. In this second strategy, I evaluate for evaluation or investigation. The first is to investigate the effect of different word embeddings, because there are some word embeddings now, the linguistic information. And the second one is the early fusion by network concatenation. So in this figure, you can see that we train acoustic feature and linguistic feature in different networks, in different model. And then we concatenate or we combine this model in after each model. So this is called as the network or model concatenation. So each modality has different their own networks, and then we concatenate both models, 2 models. And in contrast, we also can concatenate feature, so called as feature concatenation here. So instead of having 2 models, we only use 1 models, and before using 1 model, we can concatenate the feature. So between acoustic feature and acoustic feature, we could concatenate to be 1 features, and then we train both feature in the same model here. So the difference between the network concatenation and feature concatenation is in the number of model. Here only 1, and here is 2 between in different modality. And the last evaluation is the difference between manual transcription and automatic transcription from ASR output. So if we use automatic transcription instead of manual transcription, what's different in results? And the last part, or the last strategy, is late acoustic linguistic fusion, or also known as decision level fusion, because the fusion is conducted after decision for each modality. So in this case, I proposed a method by combining DNN and SVM. So each modality, each acoustic and linguistic, are trained separately in their own DNN, and then the DNN will output valence, arousal, and dominance from both modality, and then I use SVM to make the final prediction. So the input here is the output of the first stage. And we can discuss some issues here. The first is the difference between 1-stage processing with 2-stage processing. And the second one is the difference between speaker dependent and speaker independent. And the last one is the effect of removing target sentence, because one dataset we use here containing target sentence. It means target sentence is the same sentence elicited with different emotions. So because that will influence the linguistic information, we remove it. And for the datasets, we use 3 different datasets. The first is IMOCAP dataset from USC California in US. The dataset containing more than 12 hours long speech file, I think. And it is more than 10,000 utterances or turns from 10 speakers in 5 sessions. So for 1 session, there are 2 speakers. And the labels are given in valence, arousal, and dominance, VAD, scaled from 1 to 5. But when fitting into DNN, we scale it into -1 to 1. And the second dataset is called as MSP improved dataset. This from the same author of IMOCAP dataset. And this dataset containing more than 9 hours long speech file, and it has more than 8,000 utterances or turns from 12 speaker in 6 sessions. And also the level are same as IMOCAP, valence, arousal, and dominance with scale 1 to 5. And also we scale it to -1 to 1. And the last data set is come from last year Interspeed Challenge, USOM's dataset. It is the dataset of hospital in Germany, I think. And it contains stories, 261 stories. So each stories containing or dividing into many chunks. So stories, one story is long utterance. So they divided the dataset into many chunks here. For example, resulting more than 7,000 chunks or audio file. And this dataset is from more than it's large number of speaker, in this case 87 speaker, a large number of speaker on the odd people in the Germany, and the levels are given in valence and arousal, but in categorical. So L here is low, M is medium, H is high. And the difference between the dataset here with the previous research in our lab, that the previous dataset, the previous research used small dataset like Fujitsu database and also ImuDB for Germany. But here I use larger dataset, so I can use DNN. And the previous one using supervised learning. And to evaluate my research, I use CCC metric, concordance coefficient coefficient. So formulated as here, 2 multiplied by Pearson coefficient multiplied by variance of X and Y. So we compare between the prediction and the truth levels and divided by this formula. So this metric is more challenging than Pearson because we divided Pearson here row by this formula. So the score becomes smaller here. And it also gives some deviation and penalty. For example, if the original scale is from 0 to 1 and the prediction is from 0 to 5, it will give penalized. It means that the score becomes smaller. And based on the reference, this metric is more challenging because it also captures both accuracy and precision. So it's more precise than the Pearson coefficient, and mathematically and experimentally also superior to error-based loss function like MSE, mean square error, or MAE, mean absolute error here. And for interpretation, Altman in 1991 suggested that if the score is less than 0.2, it is poor. If it is between 0.2 and 0.8, it is moderate, and if it is larger than 0.8, it is good. And to close this second part, methodology, I show you the previous research in fusion of acoustic and linguistic. So my research on fusing acoustic and linguistic is not the first one, but there is already researcher proposed this idea. For example, Lee and Sri at 2002, the author of IMOCAP dataset, they proposed decision-based fusion to fuse acoustic and spot keywords using logical OR. So the idea is one of two information, acoustic or linguistic. For example, acoustic 1 and linguistic 0. So they use this decision to predict the negative or non-negative emotion. And in 2012, Karadokan and Larson also proposed the similar decision-based fusion for acoustic and lexical information. The focus is to make weighting factor here. For example, acoustic 0.6 and linguistic 0.4, or acoustic 0.3 and linguistic 0.7, or etc. So they use also different kind of linguistic information. And in 2016, Tian et al. Proposed hierarchical-based fusion to combine acoustic and lexical information. So here their proposal, A is acoustic feature, B is linguistic feature, and they input the acoustic feature to the first layer and then the linguistic feature to the second layer. And the fusing is conducted here in the second layer. in the different stage, in different level. So that's why they called it as hierarchical fusion. They also refer to the psychology-based evidence that claiming that human also use these similar methodologies. And move to the first result of our research, which is speech emotion recognition from acoustic only. The first is evaluation between local feature versus global feature. So LLD here is low-level descriptor. For example, in traditional speech processing, usually we split one utterance into many frames, usually 20 or 25 milliseconds for each frame, and then we apply it windowing function to those frames, for example, using Han or Pigman and or others, and then we calculate acoustic feature in that frame. For example, we calculate 100 acoustic feature in first frame, and we move the first frame with some overlap, for example, 50% or 25%, and then we calculate the same acoustic feature in the second frame, and we move again and again until the last frame. So for representing one utterance, we concatenate all frames. So if one utterance has 3,000 frames, so the size of feature in the end will be 3,000 multiplied by 100 features. So, and instead of using this local feature, another researcher proposed to use global feature. It means not by directly using acoustic feature, but calculating some statistical function. In this case, I propose use mean and STD based on the previous research. So if one frame has 100 features and there is 3,000 here, so I just calculate the mean value among 3,000 frames here, resulting 100 means features. So for example, MFCC or F0, so I just calculate the mean value of F0 or MFCC. So not using all frames. And using other calculation like standard deviation, I also calculate the similar. So I only has 100 feature here instead of 3,000 multiplied by 100. And then I transpose both feature, and then I concatenate them to make one vector feature with 200 dimensional size compared to here 3,000 multiplied by 100. So in the second approach, the size of feature becomes smaller, and also it may be more meaningful than using LLD. And this is the result. I evaluate this approach in 5 different acoustic feature: MFCC, LogMel, GMAPS, Geneva Minimalistic Acoustic Parameter Set, and also PAA, Python Audio Analysis, and open source feature extractor, also PAA with deltas. So we can see here that the size or dimension of low-level descriptor is huge, 3,000 multiplied by 40, for example, for MFCC, and the result is given here in CCC score, core concordance correlation coefficient. And to judge the best method, or which method perform better than others, we use mean values of these three. So this mean value is the average value of CCC score from valence, arousal, and dominance. So we can see here, for example, MFCC obtained 0.3 of mean CCC score and LogMel 0.36. So almost similar between acoustic feature here. And using mean and standard deviation, which is much smaller than LLD, we reduce the size of feature, but we obtain improvement here. For example, using MFCC, with smaller feature, we improve the score from 0.35 to 0.39 here. So the only difference here is the input only. We use the same model and the same configuration. So here we can saw that the result using mean and standard deviation using global feature is better to model the emotion within speech. In aside from the low size of the acoustic feature here, and also from this result we can see that the score of valence here is lower than arousal and dominance. So valence only 0.1 compared to dominance and arousal 0.4 and 0.4 also. So that's what I meant by the third issue. In the third issue, I stated that in the previous research, the main flex is the low score of valence prediction here, and also we spotted again in acoustic only emotion recognition here. And the next evaluation is the effect of such post-processing. In this case, I choose the effect of silence. So there are 3 treatments can be conducted regarding to silence in speed. First is by removing silence, by silence removal, and then extract acoustic feature from those silence removed region. And then the second one is by keeping silence. This is the traditional way. And the last one is by utilizing silence. It means that we still keeping silence, but we calculate the silence region as additional feature, as calculated here by such methods. And the result is shown here between among those 3 approach. I evaluate 3 conditions in 2 data sets. First, in IMOCAP data set, using removing silence, either removing silence or utilizing silence lead to better performance than the keeping silence in the traditional way. So we can see here that either removing silence, so silence affected to the performance of emotion recognition in both dataset, in IMOCAP dataset and in MSP improved dataset. And also in MSP improved dataset, the result of removing silence is the highest one, right? While the previous one is the highest one is the by utilizing silence. So we can conclude here that we can predict actually, because the difference is only small, silence may contribute to the emotion recognition, because if we remove silence or we add silence as additional feature, it gives such improvement compared to the baseline by using keeping silence. And the next one, or the last part in the first method, this first strategy, is aggregation method. So this is the common problem in many-to-one problem. For example, if we have 10 data, so to choose one data to represent 10, usually we use the most frequent one. That's called as the majority voting. However, I think that we need to investigate another method aside from my main goal is to make the acoustic and linguistic has the same one factor, so I can combine. But I think to achieve this one, I need to aggregate feature instead of output. So that's the reason is actually to make this data can be concatenated with linguistic. But I also think that humans usually use this kind of clues. For example, in one modality, usually we use the main value or the highest value to predict the emotion in perception. Maybe that works also. So I evaluated 2 different approaches here: mean values and maximum values. And the baseline is majority voting given in the baseline paper in Interspeech 2020. And here is the result. So this is the acoustic feature used in Interspeech 2020 in emotion challenge, elderly emotion challenge. And the left part, the majority voting here, is the results given in the baseline paper. They use accuracy to measure the performance of valence and arousal prediction. And I added my 2 approach, mean aggregation and maximum aggregation. So we can see here that the result for either mean and maximum value are used generally better than majority voting. For example, here using compare speech input speech features, we improve from 33 to 43. And also we can see other feature here. We can see almost all feature improve the score on the accuracy score, and also not only mean but also for maximum aggregation also. So we can say that using input aggregation is better to model from chunks to story. So from small speech data to big in speech data. And based on the first strategy, first sub-goal, I can conclude that the proposed solution from the following issue. The first is region of analysis. I propose to use utterance or global feature or HSF instead of frame-based processing. And for silence region, either removing silence or utilizing silence lead to better performance than keeping silence. It means that we predict silence contribute to emotion recognition. And finally, for the aggregation method, our results shows consistently that feature aggregation or input aggregation are better to model chunks to stories or to long utterance. However, we still see some data in the previous data is result that the prediction of valence is lower than arousal and dominance. So speech emotion recognition by using acoustic feature on is not enough here. So that's why we propose the next method, the next second subgoal, that is fusion of acoustic and linguistic at early fusion. And there are some investigation in early fusion. The first is our proposal method using multitask learning or MTL by concatenating network from acoustic and linguistic. In this case, we proposed to combine acoustic and linguistic models using different acoustic feature. We evaluate a PA and GMAP feature and also different linguistic feature, 5 linguistic feature, and then we concatenate at model level or network level, and we at the last layer we add 3 1-unit dense layer or fully connected layer to predict the degree of valence, arousal, and dominance. So here, because the goal is to maximize CCC, so we use the opposite CCCL, CCC loss, 1 minus CCC. So we minimize this loss. So we make this CCCL to be 0. So if here is 0, so the CCC become the highest one. The highest one is the 1. So 1 minus 1 will be 0 here. And because there are 3 dimensions or 3 attributes, so we sum up CCC loss function from 3 attributes, CCCLV from valence, CCCLA from arousal, and CCCLD from dominance. And because research and psychology show that there is interrelation between valence, arousal, and dominance, we add 2 parameters here to model the interrelation between valence, arousal, and dominance. So we add alpha for valence and beta for arousal. And for dominance, the factor is 1 minus alpha minus beta. So dominance is depend on valence and arousal, but between valence and arousal is independent here. We search independently. And also we investigate another approach with 3 parameters. In this case, we add alpha for valence, beta for arousal, and gamma for dominance. In this case, the interrelation between valence, arousal, and dominance are searched independently by using alpha, beta, and gamma. So we search the value of alpha, beta, and gamma from 0.0 to 1.0. We use linear search in this case. And the result is shown here. So this is the difference between no parameter, 2 parameter, and 3 parameters. And we obtain the highest one with 2 parameters, so only using alpha and beta. And the difference actually is small between 3 models, but we measure the significant difference. We run this experiment 20 times at least for each parameter, for each model, and we obtain that the difference is significant between each model, although the improvement is small. And also here we can see that now we have score of valence comparable to arousal and dominance. Previously, we only obtained 0.1, and now by fusing acoustic and linguistic, we obtain a huge improvement here. So the score of valence now become comparable among valence, arousal, and dominance, because valence is the most important dimension in emotion. So it is worth of study to improve the prediction of valence. And the optimum parameter for uniminable parameter is 0.1 for alpha, and beta is 0.5. It means that for dominance, it is 1 minus 0.1 minus 0.5 or 0.4 here. And for linguistic, the alpha is 0.7 and beta is 0.3. And if we combine or we fuse acoustic and linguistic, the result by linguistic information is used here, because we also start using both modality, the fuse of acoustic and linguistic, and we obtain the optimal parameter is one that used by linguistic information. And next, move to the evaluation of difference between manual and automatic transcription. So in the previous result, we saw you the result from manual transcription. So it means the linguistic information is obtained directly from the text transcription given by the dataset, by the author of dataset. And in this result, we presented results in which the linguistic information are obtained directly using automatic transcription. In this case, I use deep speech from Mozilla version 0.8, and then from transcribed text, I extract the linguistic feature and then input that linguistic feature to classifier. And for acoustic, it is same as the previous, and I concatenate two models here, and then use one unit dense layer to predict the degree of variance, arousal, and dominance. And the results are shown here. Using linguistic only, it still give the moderate result. For example, here by manual transcription, the dark blue one, we obtain CCC score of 0.361 using word embedding, and if we use pre-trained word to factor, we improve it, and the highest one is by the glove. But if we use the automatic transcription, the score become lower, and almost all linguistic information give the similar score. So as predicted, here the score of ASR is lower because some word error rate here produced by or generated by ASR. But still, if we combine linguistic with acoustic, in this case we use PAA with deltas, the score is improved here. So the yellow ones is the fusion of acoustic with manual automatic transcription from ASR. And the next one, or the last one in this second subgoal or second strategy, is the concatenation of acoustic and linguistic at feature level. So in this case, I use the USOMC dataset from Interspeech last year, and one factor acoustic feature and one factor linguistic feature, I concatenate them together and then input those feature into SVM directly. And then we can evaluate the difference between fusion of acoustic with the unimodal. For example, here, using the baseline model, using acoustic feature ResNet 50, the accuracy of variance is only 31, and the prediction of arousal is 35. And using linguistic only, PLLTT from transformer model, the variance prediction is high because the linguistic contribute to variance prediction here, and also the arousal also high here. But if we fuse both acoustic and linguistic here, for example, using Librusa and GMAX, we improved the score of accuracy in development from 31 from acoustic to 58, or from 49 to 58 in using fusion of acoustic and linguistic. And for arousal, we improve it from 35 from acoustic to 52, or for 40 from linguistic to 52. However, in test set, we only obtain improvement in variance only. So here the variance prediction from acoustic is 40 or 49 from linguistic, but we improve it to 56 using fusion of acoustic and linguistic. But in arousal, the result is the same one. But in development, we improve it. So from this second stage or second subgoal, we can conclude that network concatenation by fusing acoustic and linguistic improve emotion recognition in several ways. The most important is the prediction of variance, and also we can use the MTL or multitask learning to predict the variance, arousal, and dominance simultaneously. And the best model is obtained by using two parameters. And for automatic transcription, we observe that no big difference by using different linguistic model. And also by concatenating feature, we also improve, and the improvement also on variance only in test set, but in development, we improve both variance and arousal. So next to the last part, the last subgoals, which is late fusion of acoustic and linguistic information. In this late fusion, I proposed two-stage processing by combining DNN and SVM. So for each feature, for each information, I trained separately, for example, acoustic network using DNN, one DNN, and another linguistic with by using another DNN or another networks. And then each DNN resulting in prediction of variance, Rosa, and dominance, also from linguistic also. And instead of manually decide which one is the for the final prediction, I use SVM to make the final prediction. And I've evaluated three acoustic in feature here: GMAP CLD, GMAP HSF, and GMAP HSF with silence. And for linguistic, I take the highest three linguistic information from the previous result. And the result is given here. I divided into 4 scenarios. The first is IMOCAP SD, speaker dependent, and then leave one session out or speaker independent. And also for MSPIN, this part of MSP improve, which I remove the target sentence. And we got the similar results, but it is improved from the previous early fusion. For example, in the previous early fusion, we obtained the highest result is 0.50, but now we obtain 0.5 through here. And we also improve the prediction of variance here. So I think now is better than dominance. But in this case, the last case by MSPIN speaker independent, we obtain still low score on variance. And we assume that in this case, there are still effect of target sentence, although that we already removed that target sentence. And this is the relative improvement. It means that comparing two states with single states from DNN only. So from the first state, we also obtain the results. So we can see here in AMOCAP dataset, we almost obtain improvement about 30% to 40%. And in MSPIN dataset, we obtain improvement smaller, about 5 to 15%. So the different here can be explained that the first is IMOCAP dataset is larger than MSPIN dataset, so it's about more than 10,000. But MSPIN dataset only 6,000 only. And the second reason is that IMOCAP is acted, although it is also containing spontaneous speech, but still fully acted. While the MSPIN dataset is some of the dataset is spontaneous speech. And there are some discussion here that the first is the significant difference between speaker dependent and speaker independent. So we cannot use the speaker dependent to judge the performance of emotion recognition. So in the future, it is encouraged to use speaker independent because in real case, the case is very, very speaker independent. And the next is the effect of removing target sentence, although we already removed, but we still observe by low score of valence in the speaker independent scenario in the MSP dataset. So it is necessary to make further investigation for future research by using lexical control dataset. It means that without linguistic information and then small linguistic information and then more than linguistic information. So what's different between with and without linguistic information, with different size of linguistic information? And from this the last part, it can be concluded that the late fusion approach works better to model the fusion of acoustic and linguistic for fusion of both information. And as in early fusion, also in late fusion, we improve the score of variance prediction, while we also improve the score of valence, arousal, and dominance. And also, it is found that speaker dependent and speaker independent is significantly different. And the last one is although we remove the target sentence, we still observe it in our result. And come to the last part of this presentation, that is conclusions. The first is the comparative analysis. So here I show you the table of result in this research compared to the other research. So the first two rows is result in this research. The first one is the acoustic only, and then the early fusion feature level, and then late fusion decision level. And we can see here the difference between acoustic only with acoustic and linguistic. So we improve the score from Valence actually, but this result is used. This result use different model. For example, the first one is using MLP, while the second and third one using LSTM model. I just observed that using MLP is better here. So if the second and third using is conducted using MLP, so it also maybe give better result here. And also we can combine or compared to the other research, for example, using the similar data set, but here is speaker dependent. So it also obtain the similar score, I think, higher score in Valence, but lower in Rosal. And they also added two more information, that is age and gender. So these two information maybe contribute to the obtained score here. And also they use speaker dependent, and in our result, in my result, that speaker dependent usually and almost better than speaker independent, but we cannot use the speaker dependent to judge the performance of emotion recognition. And also we can, if we compare with acoustic only with different dataset here, we obtain improvement, we obtain better result in Valence here. And if we compare with other modalities, the fusion of other modalities, for example, if we add visual here, the score is improved here. So if we use additional models on this additional information in my research, I also will improve. But the benefit here, I only use acoustic and linguistic, and both information can be derived from speech only without addition of other modalities. So this is the conclusion of my research to solve the research goal, to answer the research goal. The first is it is necessity to fuse. Yes, it is this study reveals the necessity of fusing acoustic with linguistic information. And we saw that the late fusion model, the fusion of acoustic and linguistic better than early fusion and unimodal analysis. And for answer of the 5 issues, the first is region analysis. We propose to use high-level features. And for the effect of silence, we propose to remove or utilize it as additional feature. And for issue related to low valence performance, it can be improved by using fusing of acoustic and linguistic information. And for the necessity of fusing acoustic with other modalities, yes, it is necessary because our results show that's necessary. And for fusion framework, that our results shows that late fusion model fusion better than early fusion and unimodal fusion. And there are some contribution from this research. I divided in two. From acoustic only, it contributes to to strengthen the previous research, previous finding that mean and standard deviation contributes to emotion recognition. I mean, from the feature to from the global feature to local feature. And also we predict the contribution of silent pause regions. And the last one is to model chunks to stories from short utterance to long utterance. It is better modeled by feature aggregation instead of majority voting. And there are also some remaining works, for example, to investigate the more thoroughly the effect of silence. We can use another feature like temporal fan structure, and also we can fuse LLD and HSF, because to obtain HSF we need to calculate LLD first. So why not we fuse these two information for future. And for fusion of acoustic and linguistic, this study contribute to the several insights. The first is we can simultaneously predict the variance, arousal, and dominance by using multitask learning based on CCC loss. And our model shows that the interrelation between variance, arousal, and dominance is better predicted or better modeled by two parameters. And also we saw that late fusion approach is better than early fusion to model the fusion of acoustic and linguistic. And also the contribution of linguistic is to improve variance prediction, while acoustic is highly influenced arousal and dominance. It means that in the previous finding only arousal only by acoustic and linguistic improve, but we also suggest that acoustic also dominantly predict the dominance also. And there are some remaining works like the fine-tuned PRT. In this case, in this research, I only use pre-trained PRT from Google. And also if we use lexically controlled data set, it means we without linguistic information and we add information, linguistic information, small from small number to high number, what's different. And for future research, I propose the following research area. Maybe the most important is the last one is about model generalization. I think also the common issue in pattern recognition. It means that one model works in particular data set should be works better also in other data set. But nowadays, still, if we apply the same model to different data sets, the result is not similar. It's not common. And this research is gathered from this publication. The early fusion is from the first publication here in Namsipa transaction, and the late fusion is from speech communication. And for acoustic only emotion recognition, we gather the result from the following conferences. I think that's all. I give it back to Akaki Sensei.
Thank you for your presentation.
No, I think no. Mute, you mute. Okay.
Mute.
Okay, yeah.
Can you hear me?
Yes.
Okay, so Mr. Dada, thank you for presentation. Okay, next, we are moving on the question and answer time. Okay, so you can ask Mr. Atmaja via microphone directly or chat box, using chat box. Okay, first, I would like to ask the audience, are there any questions from the floors? Any questions? No question? Yeah. Okay. Can you hear me clearly? No?
I think now it's good.
Now it's good. Okay.
Yeah.
No questions?
I think from Transang this question.
Okay. Let's start.
From Transang, I think.
Tran,
Yes.
Mr. Tran, you can ask. Okay.
A question.
Okay, if there is no questions from the audiences, from the floors, we are moving on the next. That is the final defense and the final examination. No questions? Okay, so for the final defense of final examination. Okay, so that is the closed session. So I would like ask the audiences to quit or go out this meeting room.日本語で言います。次に最終試験に入りますので、審査員以外はこのから退出してください。Next session, the final defense is a closed session. So I would ask the all to quit or go out this meeting room, except the reviewers.
久保先生、強制排除できますよ。
はい。
強制排除。
はいはい。今から強制排除を始めようと思います。はい、それでは、今、審査員と後村君、だけになりました。それでは、これから、最終試験、ですね、ファイナルディフェンスに移ろうと思います。皆さん、ご質問とかあれば、随時、マイクをオンにして、質問をお願いします。
はい、先生、よければ私、一緒に。
はい、ダーニーさんどうぞ。
はい。はい、英語で質問が。バグさんと。はい。I have two questions after the previous second examination, and then now is the promotion defense, the last defense. The first question is that perhaps I haven't seen any consideration whether the proposed method is going to be working in terms of cultural background of the speaker. Because for example, in Japan itself, there are Tokyo band, and there is a speaker who has Osaka band. These are two different accent, and perhaps through my experience that these two groups express their emotions quite rather differently. And not to mention, for example, if you use in English, in America and in British English, these are two quite different, although they are English. These are two different cultures. They express their emotion differently. Not to mention Indonesia, we have 300 tribal language that express differently. Do you think in the future that it's going to be something that we have to look into deeply, that we have to include the cultural factors?
Okay, for this question that's about the cultural, or I think dialect or peng in Japanese. Yeah, I think that although different dialect has different, different style of emotion, that based on the professors that it is possible to generalize the emotion, because if, for example, if someone angry, the characteristic is the high pitch, for example, but maybe there are also some acoustic features that discriminate between one culture to another culture. But using the generalization, also the previous research in our lab also using multilingual, so we can obtain the commonalities or the similarities between one language to another language. So still it is possible to recognize the emotion regarding the dialect or the tribe or the language. But maybe if we add the specific characteristic of the style, like peng, we can improve the recognition rate. So my answer is yes, still possible without so we can make all for all dialect. But if we know the specific, maybe it will contribute better. Maybe it's such improvement only.
Okay.
So that's my answer.
I will not have the follow-ups, but I would like to ask you the second question. Do you think we need new metric rather than just using valence, arousal, and dominance? Because I think, for example, if basically my research is also dealing with speech emotion as well, but in order to make sure that our emotion guess with statistical or machine learning method is accurately correct, we also involve human expert judgment. It means that perhaps in my experience recently that the human expert judgment is a bit different with the statistical or machine learning prediction. And it's also not only small gaps, but I think it's a huge gap. Because the perception plays key roles as well in recognition of a speaker emotion. What do you think about that? Because there is currently discussion that we need more space. Space here is space of feature space. That we need more than just valence, arousal, and dominance. Do you have any comment on that?
Yes, I think, yeah, based on the last paper, they proposed the title is 4 not 3. So the title, I think the word of emotion is not 2 but 4. So they proposed the 4th dimension as expectation, and I think it's already in my dissertation book in chapter 2. I think in emotion model that coincidentally this also they propose this fourth dimension, that is expectation or predictiveness, and in previous emotion challenge they also adopted it in the challenge also. They give the levels of the predictiveness which is similar to the expectation. So yes, I am agree that maybe the fourth model is the best one, and according research in psychology also now the Geneva emotion wheel, I think they proposed also the fourth dimension also. So they make correlation between categorization and the dimension. So that's maybe that will improve the future research if we have the fourth dimension. But the problem here is the availability of the labels, because nowadays until now the dataset is still limited, and I think I cannot find the dataset with more than 3 labels. And that's for the dimension. And for the difference between machine learning and human perception, because yes, as I said in the presentation, that's the main problem why speech emotion recognition is difficult, because the labels are given by annotators, not by direct measurement. So I propose in the future, if we measure like using physiological or psychological measurement, and also some psychologists researchers also propose the 4 basic emotion, not the 5th basic emotion, but they cannot explain what is the 4 emotion is. They only show the data or the visual representation. So if the labels is based on measurement, not based on the annotation, I think it will better to model, because sometimes human perception is different between one and another, like survey. So the current technique to tackle this limitation is to use a large number of writer or annotator. So if the number of annotator, for example, 20 annotator, so the agreement become hikes and the data or the labels become reliable. So that's the current approach to tackle this limitation.
If I may, a small follow-ups. What do you, if I may, Sensei?
Yeah.
Right, just a small follow-ups. What do you see your research at the moment in terms of 5 or 10 years from now?
Okay, so in this research, I prove that linguistic information, like because it can be used in semantic analysis, and a lot, maybe almost all companies, Google, Microsoft, Amazon, now use it as linguistic information, semantic, and so what we type recorded by Google and recorded by others, and I prove that this information is related to emotion, the human emotion, but my current finding that it takes steps to fuse in the last method using lead fusion. It's too complex, I think, to be implemented. So I think I just saw that this fusion is very useful. So let's, the next step is how to make it almost word real time. For example, now we need to speak ASR, and when we directly obtain the text, but I need to extract this text to obtain the linguistic information. So in the next maybe 10 or 5 or 10 years, maybe we need to make this process less complicated, so the runtime or the processing time is becomes smaller, so it become applicable in technology. So to reduce the running time or processing time.
はい、どうもありがとうございます。以上です。
Yeah. Next, are there any comments or questions? Do you have any comments?
Hello.
Yes, I can hear.
you hear me?
Yes, Wong Sensei.
Okay. I have some questions for decision vision. First one, so which deep learning based structure did you use?
So structure, okay.
So which deep
DNN.
learning structure? Yeah.
Lumbia, close to the microphone.
Okay, maybe. Hello.
Yeah.
Yeah, this okay. This time is
This
okay.
okay. So for decision vision, so
Yes.
which type of deep learning based method did you use? For
Okay.
example, full connection or
Yes.
LSTM or CNN.
Okay.
Which one and why?
So I show you my last two slides. That's the for GNN. So for acoustic, both acoustic and linguistic, I use the similar LSTM networks here, because the acoustic is temporal data. So usually we use LSTM for temporal data, while CNN for image-like data. And I use 3 LSTMs. The first is shown here. The first is containing 47 nodes. Actually, the number of nodes is same as the number of features. So if number of feature 60, usually I use 60 just to capture the one-to-one relation. And then I use larger units, 256 units for the second and third LSTM. And then I fed the last layer. Usually I use the not the five, using the not the all the output of last layers instead of the final prediction only, or the final layer. Usually we can use this final or all in this case. And then after that, I split into 3 dense layers to predict the degree of valence, arousal, and dominance here. And using some dropout maybe 0.3 or 0.2 is, if I remember. And for linguistic information, I did the similar. Actually, I also compared with CNN, but using one DCNN, the result of LCM is better, because the modeling inside this process. So the difference here is on in the first LSTM layer. So in this case, because I use 300 dimensional from word vector, the size is 300, so I use 300 units from the first layer, and the second, third layer is similar to LSTM. And in this case, I didn't. I returned the final prediction only in the last LSTM layer, and then use dense layer, and then dropout layer, and then use 1 unit dense layer to predict the degree of valence, arousal, and dominance. So this is the architecture of LSTM, the DNN I use in 2-stage processing here.
Okay, and so far I think there are many researchers use CNN for speech emotion recognition. So did you compare your results with LSTM and CNN?
Yeah.
Many researchers found that CNN also can obtain good performance.
Yes. The result is almost similar. Yes, I compared, but not in dimensional, in categorical emotion recognition. I think I published in this APSIPA 2019 the result between the comparison between LSTM and CNN.
Okay.
And I obtained LSTM better than CNN.
Okay. And my third question is related to the first one and second one. So in this study, you use the same structure, LSTM for acoustical and the linguistic information. So
Yes.
why do you use the same structure? Because for audiovisual emotion recognition, many researchers use different neural networks. for these two modalities. So why acoustic and linguistic can use almost the same structure?
Okay. Yeah, the reason is, I think in the future, if we want to implement this architecture in real time, for example, in cloud or in hardware, we need to consider about the software parts. For example, if we use different architecture, we need to load, for example, to import. I mean, to import CNN models. So my consideration is because using the same architecture, same model, same only, we don't need to import CNN. So in software engineering, I think if we want to implement in the real time or in the cloud, so we don't need to import another model. So it becomes in production, we need to as small as possible size of program or software. So that's my reason at that time to choose this architecture.
Also, okay, I see. And I think if in the future work, if you have time, I suggest you to use different structure because maybe this can improve the performance. Okay, this is all of my questions.
Okay. I continue for the
じゃあ、
question.
当先生、はい。
Hi. So, two comments, one question. The comment is from the small question is the English sometimes is very boring. So you have to spend more time for polishing English. For example, I just tell you one example for the okay. I think in your the 7 the
Page 7.
chapter 7, just chapter 7 at the beginning, you said what you said. Okay, it's very boring. Yeah, it's not like the doctor thesis. You said to the end, several methods have been proposed, several results have been obtained. Yeah,
Yes.
it's very boring. It's very boring. No meaning.
Okay.
Okay, make your thesis. Your study is very interesting. Make your thesis is more interesting. Okay, this is the first comment. The second comment, I just follow Professor Wang's question. And when I first see your earlier fission and fusion and the later fusion, what I image of this architecture? Yeah, in the early one, you put the two features together, connected together, and fit into the deep neural network and make the result. And for the later one, you put the feature independently to the two neural network, and then fusion after this deep neural network. But at your first one, you didn't use deep neural network. You just use the support vector machine. Is right?
In the late fusion, yes.
Yeah, that's not a fact. That's the result not caused by the earlier confusion and later confusion, the fusion and the later fusion. It's different between you have the deep neural network use a nonlinear method or not. Do you agree with me?
Yes, yes.
So, yeah, you just use the wrong concept told people. This one is earlier fusion, is a later fusion. It's actually the essential part is not really true. Is one is linear machine learning method. Another one is nonlinear machine learning method.
Yes.
So you have to correct your base part for this, how to give the direct description, give the correct the meaning. It lets the reader to understand what's the essential difference between your two methods. Okay.
Okay.
Okay. Yeah, that's two comments. My question is, so yeah, it's very good to combine this acoustic feature and this textual feature. So, you know, a few years ago, someone is from the a psychological point of view to investigate what's the textual features effect for the emotion. Okay, this result in their study. They said the result showed if this texture is a positive meaning, you can very easily to modulate, use a different emotion, change the emotion of this sentence. If this texture meaning at the beginning is negative, it's almost not possible to change this negative sentence to be a positive sentence. That studies result. Okay, yeah. If that study's result is true, I want to know what's happened in your study. Yeah, you use the textual information get better.
Yes.
Okay, so which part is get better? Is any part get worse or not? That's my question.
Okay, thank you for the question. Yeah, so as long as I understand, so in research in psychology, if the sentence is positive, so it is easy to judge the emotion. If negative, so it's almost not possible. So I think I ever read that paper. So that's based on the negative or positive of words like lexicon, like in there is a dictionary, lexicon dictionary. So
not a dictionary. That's a sentence. That's by human subject. The subjective evaluation. That research. Okay. This is not by the this word vector.
Okay. So that's I think the one. Can I show my slide? The kind of acoustic feature, the textual feature used in that research is like in. Sorry, this one. So, yeah, in the sentence they calculate the negation and maybe some. Maybe I think they use some emotional words to count the in one sentence. So the information, the textual information or linguistic information is they calculate. I mean they count the negative or positive of emotion.
Okay. Make my question strict. I believe it. Yeah, yes. My question is, did you think what's the improvement in your study no, you just give the general result. Okay, it's from the 0.5 to 0.53. Okay. Yeah, my question is, maybe you should reference this kind of knowledge to find what's the improvement in your study. Maybe some part is not, is damage. It's possible.
Yeah.
So that's my question.
Yeah. So my comment is, that's different. The acoustic, the linguistic feature I used here is from word vector. So not by counting negative or positive or words. So if I obtain that information, so if from sentence or from words I get additional information about the polarity of these words. So yeah, it compared with my current linguistic information, I believe it will improve the performance because we know the polarity of the words. So that will improve, huge improvement, I think.
That's in the final part. The final part, you get the two acoustic one, you get the three dimensions for the emotion. From the text, you get the three dimension emotions, and you put it together and use the support vector machine. But actually, in that part, if the texture told you the negative sentence, maybe they should have more weighting coefficient. But not just by the distribution alone. Okay.
I got the idea.
Okay, you can think in this way. Maybe for that part, from this one and from the texture result and for the acoustic result, for the different sentence, maybe we should use a different weighting coefficient. That's my point. Okay.
Thank you. Thank you very much, Sensei.
白井先生、榎木先生、白井先生、コメントありますでしょうか？
Okay. I have two questions. In my understanding, the main contribution of your thesis is to fusion of the acoustic and linguistic features. On the other hand, you show page 23, you show some previous work that also use both linguistic, acoustic, and linguistic features. Can you clarify the difference of your method and this previous work again?
Okay, thank you very much, Sensei. And the difference, the idea, I think the same, the fuse of acoustic and linguistic. The difference is, so one by one, I think the idea is same, but the concept and philosophy, I think, is different. So first, my concept is I combine, I fuse information, in this case, features, acoustic feature and linguistic feature at different approach, late and early fusion. And for example, in this one, in this first study, they use actually not linguistic because only spot keywords. So if in the utterance they detect, they spot some keywords, so it become negative or positive. And they just use logical or 1 or 0. So if acoustic 1, linguistic 1, it become 1, so positive or negative. If acoustic 0 and linguistic 1, so it become also positive. So that's the idea and the concept in the first in this literatures. And in the second literature is the concept is to weigh between acoustic and linguistic feature. So, and again, the linguistic information here is different because they use semantic information from dictionary and new dictionary. So in this dictionary, it already contains the value, the score of valence, arousal, and dominance. So they use two approach or two semantic information here, LSE and NU, and then they add these two value, and this is the one. This is a linguistic information, and using an acoustic information, they experiment with some weighting functions here. Here, for example, the sum should be 1. So, for example, 50% from acoustic, 50% from linguistic, or 40% from acoustic, and 60% from linguistic. So, again, the concept is similar, but the idea is the idea is the same, but the concept is different because the linguistic information here is come from dictionary and some handcrafted features, and I use the word vectors, word embeddings, so to represent emotion within sentences. And in the third study here by Tian et al. Here, the idea is the networks actually. So they claim that based on psychology that our brain process information in multi-step or multi-stage, different level. So they input acoustic feature at first layer, while linguistic information is in the second layer. And again, this linguistic or information here is lexical features similar to the previous one, like from dictionary. So although the idea is same, fusing acoustic and linguistic, but the concept is different, the approach is different. So that's my answer, I think.
That's okay. So roughly saying the basic idea is the same, but how the model or method or approach is different. So
yes,
the question here is which approach or which method is better to combine or fuse these two kind of features? Or in other words, is it possible to directly compare your method with this method with using the same data set?
This all three data sets use this different data set. Also, the metric is different and the data set is different. But the second one also using MSE, I think mean square error, MSE and MAE. This two regression model, and I compare to this one. My model is better in terms of MSE and MAE, so I can compare directly with this one. But the second and third, I cannot.
Okay, hi, thank you. So another question is that in your result of experiment, you reported that your method, CCC of your method is around 0.5 or 0.6 or so.
Yes.
But I'm wondering how good it is. In the beginning of the presentation, you said if the CC is greater than 0.8, it is regarded as good. Yeah. But so, of course, your method can improve the performance of the emotion recognition, but it is not so good enough for for real application. So my question is how do you think your method is how useful for your method for real application?
So you mean how could my result or my methods compare to this result, because still smaller?
What I want to say that if the performance of the system is low, it is rather difficult to use for some application. For example, the dialogue system or something like that.
Yes.
So my question is, what is the possibility of your method to apply some real approach?
Okay. I got the question. Yeah. Yes. If we compare this result with, for example, another task, it is lower than the actual the actual results in another task. So my comments here is that this is from statistics, and usually in statistics we play with the measurement. For example, for example, the common example is use the tall or the weight of the pupil and then make some correlation. But as I said in the previous, that the level here is the level of dimensional emotion is not exact here. So I think the problem here is in the dataset, because I still see, and I already reported to the author, that some labels didn't has any value than below 0 and higher than 5. And in some cases, they only use 2 annotators in IMOCAP dataset. So I think to make the possibility high, we need to make the reliable dataset. As in Dani Sensei previously asked, so I think instead of using annotator, it is better to use labels from measurement, from physiological measurement. I don't know what measurement can be used, but instead of using labels from annotator, because it's not exact value, we can calculate the correlation between our result with the labels from measurement.
By the way, do you have any data to show some inter-annotator agreement in these datasets?
Yes, and you mean the agreement of the dataset?
Yeah, agreement of the 2 or more annotators on the dataset.
Yeah, I think in the reference, in the last one, I so here they use the similar. I think this dataset IMOCAP podcast. This is an MSV Improv is from the same author, and yeah, this one, the fourth one and the fifth one actually from the same author here, and they doubled the number of data set to make a balance and the labels, because the level of finds, arousal, and dominance is not balanced. They doubled, they copy the data, so that's why I think this the evaluation, the score become high here. Aside from using additional information. And this one, I think podcast is more reliable data set. So the number of annotator is higher than IMOCAP. So if
no. My question is that, for example, two annotators decide the score of the balance, arousal, and dominance. How the results are agreed between 2 annotators? Do you know such a data?
The agreement, yes. Can
agreement ratio, high.
Okay, can I share this? So I put it in I can open the so I show you. So I show you one reference of IMOCAP data. So here the agreement between the annotator here. So they measure in Cronbach alpha. So for this is the data set I use for IMOCAP. The agreement of variance is high actually, but for activation and dominance is about 0.6 from the entire data set here.
It's not so bad. Well, I think inter-annotator agreement rates are high, I think. Okay, it is a still difficult problem for computers, I think.
Yeah, yes.
Okay, this was all my questions. Thank you.
Okay. Thank you.
宇野木先生、コメントお願いします。
はい。Atmaja-kun, may I
Yes.
repeat the same question that Shirai Sensei pointed out?
Yes.
Could you show me your conclusion?
Okay. Sure. Okay, son.
Yeah, so within the first sentence, I'm so sensitive to this representation because you say your research reveals this necessity. But according to the Shirai-sensei's questions, I think, is it true? You say your research reveals the necessity of diffusion, acoustic, and linguistic information for dimensional emotion
Yes.
emotion recognition.
Mm.
But in
Mm.
my feeling, you have not revealed. You say just your research demonstrate or just what to say, the use of the fusion of the acoustic and linguistic information can improve the performance. This is my impression.
Okay.
Is this
So
true?
okay. So my comment
But
is
still the CCC is not so high.
Mhm.
That's just from the comparative evaluations.
Mhm.
So your result is not the best for
Yes.
all already, but still you want to conclude your study revealed the necessity.
Yeah, I conclude that statement because the first is come from this the third issue, the low valence performance. So because in unimodal we only obtain 0.1. So according to the presentation of the interpretation of CCC, so it is poor, and using CCC we doubled, I think more than doubled. So from 0.1 to 0.4. So I think it solved the not comparable, not in the previous in Reda and C Lee research, there is a big gap between valence and arousal and dominance. So I think now I make it now comparable between valence, arousal, and dominance, although still below 0.6. So that's why I need, so we need linguistic, because linguistic contribute to valence. So it becomes comparable between valence, arousal, and dominance. Although the score is still lower than 0.6. So that's what I mean by we need to the necessity of using acoustic and linguistic information.
I mean, it's a so strong representation for me. So is it true? For example, the OCCC will be over the 0.8. So I agree with the idea. So the study reveals this point. Necessity. But still, you do not use to be confusing the fusing to information, but the result is very similar. So I'm not sure whether or not you can confirm this necessity in this point. This is my question. Still, the Shirai-sensei pointed out there are 3 or 4 related works. You say concept is similar or same.
Yes.
Idea is also same, but the method or implementation is different. So I'm not sure whether or not this is the philosophy is the same or not.
So what others?
This is a PhD philosophy.
Yeah.
So philosophy should be the original.
Yeah, agree. Yeah, I think the idea is same, but the concept, I can argue that the concept is different, because in this work is my concept is the information, acoustic and linguistic information. For example, in this, although these 3 works state that there is fusion between acoustic and linguistic fusion, but that's not the information according, because that's like spot keywords, which they just detect some keyword exist or not exist. If the some keyword exists, so it is negative or positive. And the second one also they use dictionary, and the last one also using lexical, actually not linguistic. So my concept is information fusion, acoustic with additional linguistic information fusion. But in the previous one is, I think that's, I can say that this is not linguistic fusion, but maybe with like keywords or dictionary, not information fusion, according to me. So that's the different. Maybe the idea is same. The philosophy still differs.
Okay. So okay. So after 10 years passed from now, do you believe? So anybody agrees with your conclusion, then still your conclusion will be existing. Anybody say your conclusion is the best, and then anybody follow your philosophy? I mean, or within 10 years, nobody refer this result.
I predict that although this my research is not the best one, but anyone will agree.
Excuse me. If this is not the best one, I'm not sure whether or not you can conclude that your study reveals the necessity of the fuse of the two information. This is quite important for me. If you have the philosophy of this work, and then you can conclude your study reveals the necessity of the fuse of the two information. Okay, I agree with you. But in my feeling, it is quite difficult for me to follow your conclusion. You have not yet revealed this point. You confirm only the use of two information. A fuse of the two information can improve the performance only. This is my impression. So I want to ask you. So I want to confirm your conclusion, and I want to check your philosophy in this work.
I predict that someone will follow me in this using the similar idea. I mean the linguistic information, word embeddings in this case, and acoustic information, acoustic feature. Maybe they use another acoustic information, and maybe currently it's not the. I can claim that currently is the best, but maybe in next 10 years it's not the best one. And for the revealing the necessity that I saw that between unimodal acoustic only or linguistic only with fusing of acoustic and linguistic, there is a significant difference both from statistical tests and also from result and interpretation. But the problem now is we just achieve the minimum border of revealing this necessity. So still I can claim that necessary based on the significant difference between unimodal and information fusion.
Yeah, but have you already confirmed the significance?
Yes, I calculate the significant difference between unimodal and bimodal.
So which page should we check?
I think in book or in presentation let's see. This one, I think. Sorry, so my current thing I can show you in page. What the difference? I think this one is. Oh, speak different dependent. I think in this one I saw but I didn't say. So let me check with. I think in my one of my paper. Sorry, I didn't find it in this.
Yeah, me too.
Yeah,
I can find that there are word of the significant or significant differences in the manuscript. But I think this is quite important for you to confirm your conclusion.
Yeah.
This is my comment. Yeah.
Yeah, I already wrote in paper. I think in journal. Maybe I need to include this one. So there is
this is quite important point, I think.
Yeah.
You should add this comment point in your manuscript, I think.
Okay, thank you.
Okay, so that's all. Thank you so much.
Okay.
Yeah, thank you for the comments. The next we are discussing about the path or fail of the final defense. じゃあ、頭じゃくん、please go out.